The point of this video is to give you a strong visual understanding of magnetic variation as it applies to navigation. You've probably heard expressions like east is least and west is best, whatever the heck that means, and they've done for you the same no good at all that they've done for me. So we're going to start a discussion from the standpoint of navigating a boat or an aircraft where you know where you are, you want to stay on course, and you want to keep on knowing where you are. Then we're going to back it out and describe this in the orienteering or hiking situation using a lensatic compass, where maybe you don't really know exactly where you are, but you want to figure it out before you get eaten by a bear. Magnetic variation and magnetic declination are the same thing. In this video, I'll use the term variation, and that's the term most commonly used by aviators like me. Now, keep in mind that true north is the belle of the ball here. That's what you need to use to plot your course or find your location. Cartographers create maps to true north simply because magnetic north is too variable and too unreliable for good map making. Problem is, all you've got is a magnetic compass. So you need to know where true north is on the basis of the reading on your magnetic compass. Modern electronic compasses exist, which use GPS to determine true north. Well, yippee for them. Lewis and Clark didn't have one of those. Neither did Magellan, Columbus, the Vikings, the Polynesians. The graphic shown here is published in training materials provided by the United States Federal Aviation Administration, so it's public domain. It shows the varying amounts of magnetic variation, or declination, as you move across the continental United States. The curved lines are called isogonic lines, and if you're moving along an isogonic line, the magnetic variation that you experience will remain constant. Similarly, if you move perpendicular to an isogonic line, you'll experience the fastest change in magnetic variation. The agonic line, or agonic line, is simply the isogonic line where the variation is zero. Magnetic variation occurs because the magnetic North Pole and the geometric North Pole are simply not in the same place. They are actually about 1,300 miles apart. So, from different vantage points on the Earth, if you could simply look north and see the poles, they would appear to be in line, one behind the other, if you're on the agonic line. But if you're up in New England, say Burlington, Vermont, on the plus 20 isogonic line, then a magnetic North Pole would appear to the left, make that to the west of the geometric North Pole. So that would be called westerly variation, because the magnetic North Pole, which is used for reference, is west of the true North Pole, which is used for navigation. Keep in mind, true north is the boss here, so we regard the magnetic reading as the faulty one to be corrected. In Michigan or Illinois, which are near the agonic line, the difference is fairly small, but on the coasts of America, or in Alaska or most of Canada, it's a big difference, and it will be the difference between getting to your destination or missing it by miles. So, how do you interpret a difference? Well, let's say you're flying this Pitcairn male wing airplane, and you want to go true north at a point where the magnetic variation is 20 degrees westerly. First, aim the airplane in the direction the compass says is north, then realize that your nose is pointing 20 degrees to the left of true north. So now make a right turn of 20 degrees. Your compass will now show a heading of 20 degrees. So now you're traveling on a true northerly heading. You're going true north. Since a right turn makes the compass read higher numbers, you can express this with arithmetic. From a magnetic heading of 0, you added 20 degrees, or the amount of the magnetic variation, to get to the true heading. So the relationship in first grade math is magnetic heading equals true heading plus westerly variation. You know that easterly variation is the opposite of westerly. It's always a negative number. So you simply need to remember that magnetic heading is equal to the true heading plus the signed, the plus or minus signed magnetic variation value. If you could have simply looked up over the horizon and actually seen the two poles, like sticking out of the ground, the magnetic and the true poles, they'd have looked like this. Oh, yeah, I see it. There's the true North Pole to the right and the magnetic pole to the left. So to steer for the true North Pole, I need to add a few degrees to my magnetic heading, and there I go. Okay, so let's look at this in a situation that's not quite as bonehead simple, where you're not just going straight north. You live in Lancaster, Vermont, and you want to go visit grandma in Saratoga, New York. You pull up the road map and, oh, that looks like a pretty rough route. So you say to the wife, let's just take the mail wing. She agrees, of course, as wives always do. So you measure the course and find that it's a heading of 230 degrees and about 143 miles. But that's the true course. You got it off of a paper map. It's the true course. So to figure out the magnetic course that you'll need to fly, fall back on that simple equation, add the 20 degrees plus 20 westerly variation to the true course, and you get 250 degrees. This is the number you'll need to follow on your magnetic compass to stay on a straight course to grandma's house. Mind you, this time you're traveling pretty much perpendicular to the isogonic lines. So the magnetic variation you're going to experience is going to change. It's going to go down a little as you approach the agonic line, and you'll need to adjust for the magnetic variation a little bit less as you go along. That process is outside the scope of this video. I think you get the idea, and they'll teach you more about that in flight school. Of course, you could do this like you did in the last example, just point the airplane until the compass says 230 degrees, then turn right 20 degrees, and whatever that number is, it would be 250. Hold that heading until you can smell grandma's cooking. If you didn't make the correction, then in the 143 miles you'd fly, you'd miss the mark by 49 miles. And by the time you find your way back to grandma's house, it'd be cold dumplings for dinner. You don't want that. So I suppose it goes without saying that if you're on the west side of the agonic line, it's pretty much the same thing, except, of course, that you'd point your airplane or your boat to the magnetic heading first and then correct for the magnetic variation by turning left. And of course, you'd still use the one equation that I gave you, but remembering that you're adding a negative number to the true course to find the magnetic course. You're still adding true course plus magnetic variation, but this time the magnetic variation is a negative number. So, up to this point, we took information from a chart, from a map. We interpreted it to be useful with the navigational equipment we have on board and used it to navigate the terrain or the water below our vessel. But now we're out hiking and we need to turn that around. We're going to use our magnetic compass to take information and then we'll interpret that information so we can go back to a chart and figure out if we're still on course. The same equations apply. But now, instead of starting with true bearings and computing magnetic, we're going to start with magnetic and compute true. I'm also going to change up the terminology a little bit, and instead of saying true heading or magnetic heading, I'm going to say true direction or magnetic direction. So I'll change the terminology in the equations like this. So dust off your fourth grade algebra and rearrange the equation we've already discussed. Now you're starting with a known magnetic direction and variation and solving for true direction. True direction is equal to magnetic direction minus the magnetic variation, remembering that the magnetic variation is a positive number east of the agonic line and a negative number west of the agonic line. Now then, you're out in the woods carrying a basket of nutritious snacks to your elderly grandmother's house. A woodsman has already killed the big bad wolf, so only the bears in the old minefield remain dangerous. You have the map shown here. The map shows an abandoned cabin to the west and an old deer blind to the north. You use your lensatic compass to determine the direction from you to those landmarks. If you've done this correctly, then you've measured 15 degrees from your location to the deer blind and then subtracted minus 20 degrees to determine that the true direction to the old deer blind is 35 degrees. Now you draw a line at 35 degrees to true north that goes through that deer blind, and you know you're somewhere on that line. Repeat this process for the abandoned cabin. Measure 280 degrees, subtract minus 20, get 300. Draw a line at 300 degrees that goes through the old cabin, and you're also somewhere on that line. Where the two lines cross is where you are. But if you did it wrong, then you forgot to add the 20 degrees to each reading. Now you'll draw lines at 15 and 280 degrees that go through those landmarks, and you'll think you're right on course, nearing grandma's house, when in reality, you're on the path to the old minefield. That could go very badly. So to sum this up, You only need to remember two things. First, the equation that converts between magnetic and true north directions, which you can rearrange to suit your needs if you're starting with map data and looking at a course, or starting with course data and then looking at a map. And you need to remember that easterly variation is always a negative number, and westerly variation is always a positive number. Hey, east is least, so that's how that works. Okay, then. Practice this a bit before you go out and use it for real. Happy navigating!